where we'll be using astronomical data to model our solar system. Specifically, we're going to model all the planets and their orbits around the sun. And we're going to use this model to predict the length of a year, a month, and a day on Earth, and the period of revolutions of each planet relative to the Earth. And my results, I found the day on Earth to be 0.9936, which is very close to 1. The month to be 30.223 days, which corresponds to a regular month being either 30 or 31 days, and then a year to be 362.67 days, which is very close to 365. So my model was pretty accurate in predicting the length of a year, a month, and a day on Earth. So here are the models that we use. Gravitational force, which is negative g times the sun's mass times the planet's mass, divided by the distance between the two bodies squared. And then we're going to assume that the gravitational force is the only force acting on the planet. So we can set this equal to F net and use Newton's second law to update the velocity, and use this velocity to update the position of each planet for each time interval. So we're going to need some initial conditions. We need the masses of each planet and the sun. We need the distance, the initial distance of each planet relative to the sun, and each planet's initial velocity. So we find that here online. So here are all the distances from the sun. Here are all the planets' orbital speeds, which we'll use for the initial velocities, and I found the masses by Googling them. So here's our code. Create a ball and a trail for each planet. Initial conditions. Here are all our masses, and then here are all our initial velocities for each planet. And the initial velocities are only in the x direction right now because their initial positions are right above the sun in the plus y direction. So at this instant in time, the planet is only moving in the x direction this amount of meters per second. So here's where we calculate the positions of our planets. For each planet, we have a block of code, and in each of these blocks, we will calculate the distance between the planet and the sun, use that distance to calculate fgrav or fnet, and then use that fnet to update the velocity and the position. And then we're going to do this for each planet for each time interval. And here is what it looks like. As you can see, you can't really see Mercury very well. Venus is in orange, Earth is blue, and then here's Mars in red, and then we have Jupiter, Saturn, Uranus, and Neptune. Alright, so we want to calculate how many days it takes for each of these planets to complete one revolution. So the formula for doing that is 2 pi times the magnitude of the planet's position divided by the magnitude of the planet's velocity divided by delta t. And then this will output here. So this is how many days it takes for Mercury to finish one revolution. Here's for Venus, Earth, Mars, etc. So we can see here that Earth, 362.67 days for a year. And then we divide that by 12 to get 30 for a month. And we divide that again by 365 to get 0.9936, or almost 1 for the day. So we can see that the model fits our solar system fairly accurately. And then we're going to take each of these values for the revolutions and divide them by 365 to get a period of revolution for each of the planets. And comparing them to the values found in the chart here, we find that they are all very similar. So our model is, again, very accurate. But why don't they match up perfectly? Well, since the orbits of all the planets are elliptical instead of circular, there may be like the position of the planet relative to the sun may be off. So that's why sometimes there will be a slight deviance for the revolution of the planet.